Hey everyone, every time you send an email, stream a movie, or jump on a video call, you're tapping into this massive, invisible web of technologies. Today, we're going to pull back the curtain on that hidden architecture that basically runs our digital lives. So let's just dive right in and see how it all really works. I mean, just think about it for a second. You click a link and poof. In less time than it takes you to blink, information zips from a server maybe thousands of miles away, right onto your screen. How does that even happen? It feels like magic, but it's actually something way more impressive. It's just brilliant engineering. You see, the speed and the reliability of our whole connected world, it's not an accident. It's the result of decades of problem solving, all focused on cracking four huge, fundamental challenges. And in this explainer, we're going to break down every single one. First up, navigation. I mean, with billions of devices all connected at once, how does one little piece of data know where in the world to go? Well, it needs a map. It needs directions. It needs a kind of GPS for the internet. This is the challenge of routing. So here's the key. Every time you send anything online, doesn't matter if it's an email or just one frame of a movie, it gets broken up into these tiny little things called data packets. Routing is the job of figuring out the absolute best path for each one of those packets to travel, from you to its destination, hopping between countless routers along the way. So this is basically showing the two main ways routers think about finding those paths. On one hand, you have distance vector. That's kind of like asking your next-door neighbor for directions. It's simple, but you only know what they know, which means you can easily get stuck going in circles. On the other hand, there's link state. This is like having a full-blown satellite map of the entire road network. Every router can see the whole picture and figure out the best path all on its own. It's way faster and a lot more stable. And here are the actual protocols that put those ideas into practice. Think of BGP as the global highway system that connects different countries, or in network terms, autonomous systems. It's complex. It uses policies, not just the shortest route. OSPF? That's more like the road network inside one of those countries, using that fancy link state map for super efficient travel. And RIP? Well, RIP's the older, simpler system. Kind of like those local back roads that, can sometimes lead you in circles. Okay, on to our second challenge. So once you have a map, every single place on it needs a unique address, right? Well, in the digital world, how do you possibly give a unique address to every single phone, laptop, and, smart toaster on the entire planet? The original Internet addressing system, called IPv4, had about 4.3 billion addresses. Back in the day, that sounded like an absolutely infinite number. I mean, we'd never run out of those, right? Yeah, we were wrong. So wrong. With the explosion of PCs, then smartphones, and now all this Internet of Things stuff, we were speeding toward a digital housing crisis. We were literally running out of room, which threatened to stop the Internet's growth dead in its tracks. The solution? A new system called IPv6, and the number of addresses it provides, it's just staggering. We're talking 340 with 36 zeros after it. To put that in perspective, that's more than enough addresses for every single grain of sand on Earth. So yeah, the address shortage problem is pretty much solved. But IPv6 did more than just add addresses, it actually made connecting way smarter. With something called stateless auto-configuration, your device can pretty much give itself an address. It just listens for the local network's zip code or prefix from a nearby router, combines it with its own unique serial number, and bam, it's online. No central server has to hand anything out. It just works. Okay, so our little data packets have an address and they have a map. But the internet is a public space, right? So challenge number 3 is all about creating boundaries. How do we keep our private traffic private? And how do we keep all our local traffic organized and running smoothly? So the first part of that solution is the VPN. You've probably heard of them. A virtual private network basically creates a secure encrypted tunnel for your data to travel through the public internet. Think of it like a private armored car service, just for your data packets. Now, there are different types of VPNs. IPsec is awesome for connecting entire office networks together securely, but it can sometimes have trouble with certain network setups that hide everything behind a single address. SSL-based VPNs, though, they're perfect for when you, as an individual, need to securely get into a specific WCAP from, say, a coffee shop. They're just incredibly flexible. Now, while VPNs create boundaries across the huge open internet, VLANs create boundaries right inside your local office or campus network. They let you take one single physical network and basically chop it up into multiple separate logical networks. The best analogy for this is a big open plan office. If someone shouts an announcement, everybody hears it. It's distracting, it's inefficient. VLANs are like putting up virtual walls. Now an announcement made in the sales department is only heard by the sales department. It keeps all the network traffic organized and just cuts down on all that unnecessary noise. All right, our final challenge. Our data is routed, it's addressed, and it's secure. But let's be real. Not all data is created equal. A video call is way more sensitive to delays than a simple email. So how do we create an express lane for all the important stuff? This really is the heart of the problem of what we call quality of service, or QoS. If every data packet is treated the same, your important video call could get stuck in a traffic jam behind someone's massive file download. And that's when you get all those glitches and dropped calls. We need a way to prioritize. And the solution is this wonderfully clever technology called MPLS. Instead of making every router along the path look up a complex address on a map, MPLS just sticks a simple little label on the packet right at the beginning of its trip. It's just like putting a priority overnight sticker on a package. And the whole process is just so elegant. The first router pushes a label on. Every router in the middle simply swaps that label for the next one in the path. No deep thinking needed, just a quick swap and send. And then the very last router pops the label off right before it reaches its final destination. This creates a super efficient, predetermined express lane for all that high priority traffic. So let's just bring it all together. These technologies, they're not just isolated tricks. They're all part of this interconnected system that makes our entire digital world possible. We faced the challenge of navigation, and we solved it with smart routing. We faced the challenge of identification, and we solved it with the massive scale of IPv6. We needed privacy and we needed organization, and we got that from VPNs and VLANs. And finally, we needed to control traffic flow, which we achieved with the express lanes of MPLS. Each of these solutions was a monumental leap forward, and each one was born out of necessity. As we move into an even more connected future, with AI, the Internet of Things, and technologies we can't even dream of yet, it leaves us with one final and I think really exciting question to think about. What comes next?